Welcome to our live training session number 42, part 6. In this video, we're going to start to work with our high cam fuel and ignition timing tuning. This is going to be our VTEC operation. So we have our VE table 1 for low cam, we've already mapped out. The VE table 2 now is what we're going to be working on and calibrating in this video. So we're going to look at doing our fuel, our spark timing, and looking at our variable cam so we can completely dial in our high cam of operation, as well as learning how to set our VTEC engagement point by reading our VE table 1 and VE table 2. There's going to be a lot of tips and tricks I'm going to be sharing with you in this video, so let's jump in so we can check everything out. Welcome back to our live training session here with our K-Series swapped EG Civic running on AEM Infinity. In the last video, we optimized the fuel, spark timing, and variable cam on our low cam of operation. In this video, we're ready to take a look at doing our Vtec tuning, learning how to program all of the tables associated with our high cam of operation, also programming our Vtec and taking a look at a couple other things that I want to cover here in the video that we didn't get to cover in the last video. So the very first thing I want to point out here, we have this parameter in our logging list in our text grid here. It's called mass airflow. Now, if we look at a mass airflow sensor that's registering the amount of air mass that's coming into the engine or airflow that's coming into the engine, they're very, very accurate as long as we have other details and scaling factors right. So if you're unfamiliar with a MAP sensor, you're going to find those on most OEM applications have a mass airflow sensor. It's going to make tuning much, much easier. Now, we did do a MAP specific AEM Infinity live training video that's going to be in the Porsche Cayman in our course library. Now, in that video, I was referencing what the mass airflow sensor was flowing in units of pound per minute. And if we know what the pound per minute range is, and if it's accurate, we're going to find if we multiply this value by approximately 10, we're going to find we can translate that into the horsepower the engine is making. So some things that are going to be important here to kind of note in the mass airflow parameter, when we're in speed density without a MAP sensor, it relies on what's coming from our actual VE table here. So these values represent the cylinder filling that's going on in our engine, because we know the engine displacement, we know what the air temperature is going to be, we know what all of our injector data is going to be, we know what the MAP pressure is going to be reading. All of that takes into account what is going on with our VE fuel calculation. Because this is going to be estimating the airflow, the values in the table, therefore the parameter here, mass airflow in units of pound per minute, is still valid in a speed density application when we're not running an actual mass airflow sensor. So in this situation, we can use this as a check, a cross check to the values that we have programmed into our table. Are these values logical or not? That depends on how well this mass airflow, a representation of air coming into the engine, is going to be lining up to the horsepower the engine's making. So if we take a look here, the mass airflow showing 21.35 pound per minute. If we multiply this by approximately 10.2 is the actual conversion factor, we're going to find the engine should be making around 220 horsepower. Now, if we take a look at the dyno graph, our very last pull showed 219.5 horsepower. These are all the previous low cam pulls that we're finding here. So that's the power it was outputting, roughly 215 to 220 horsepower, which backs up exactly what we're finding here in the mass airflow representation, or what it's simulating coming from our table here, which means the VE values in our table are going to be accurate for this engine. If we found that this was really low or really high, and these values were kind of all over the place, we would find that we wouldn't have represented the actual airflow coming into the engine, which can be a result of having the improperly programmed engine displacement or injector data. Remember, we had to go in and start to skew the injector data. I went in from the injector data sheet from Injector Dynamics and I used the values. We ended up having to drastically change these to get our VE values when we started off doing our tuning process back in line to where they needed to be. So these values are a little bit higher than what I would normally expect from a K-Series engine. However, this is highly efficient, so it's going to be commanding and demanding more higher VE values because we have higher cylinder filling going on above and beyond what we would find on a typical K-Series engine. So this allows us to do a checksum here, kind of getting a feel for our VE values in our table if we've programmed them properly or not. So in this case, we have. It's lining up almost within 5 horsepower of what it's showing here on the actual dyno graph. So I'm confident in my VE values. So that's just one thing I wanted to point out that I didn't mention in the last video. So now we're going to be looking at doing and mapping out our high cam operation. So we need to do a couple things. First, we're going to copy our VE table 1. This is our low cam fuel table. We're going to copy this and paste it into our VE table 2. This will give us a better starting point than just starting off. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.